When a chemical reaction takes place, it's hard to imagine it doing work, but that's precisely what a reaction that produces gases does. If you can imagine, say, doing an experiment where you mix vinegar with baking soda, you always get bubbles forming. Almost every child has tried that experiment. Now, if you can also imagine that reaction taking place in a vacuum, it's easy to imagine that the gases expanding from the reaction would have an easier time coming out of the reaction surface if there's no air. But typically, when we do experiments on the surface of the Earth, there is an atmospheric pressure that the gases being produced by the reaction have to work against. And this is where we get the term P delta V. P is the pressure of the atmosphere, which the gas has to work against to come out of the reaction surface, and delta V is the amount of volume it ends up occupying after the reaction is over. So we can imagine a reaction where gases are being produced and the gas is pushing back the atmosphere until it reaches a height h, and that height delta h multiplied by the area of the surface that it has pushed away is equal to the volume change of the reaction. So this is where we get P delta V. Now, P delta V can also be seen as work. This is work done by the gas, and we give it a negative value because the work is being done by the system on the surroundings. So that the sign convention tells us that's a negative amount. That's negative work being done by the system. It's interesting to point out here that pressure is a force applied over an area. So it has units of newtons per meter squared. Volume, which is the volume swept out by the gas, has units of meters cubed. So when you multiply those two quantities, like we do in P delta V, meters cancel, you get newtons times meter. Well, newton meters is also known as joules, which fits in nicely with our theory that the gas is doing work. So the units of work is joules. Now, if a process takes place at constant pressure, say in an open beaker exposed to atmospheric pressure, we get this relationship. Delta H, also known as enthalpy, is equal to delta E plus P delta V, where delta E is the internal energy of the chemicals involved in the reaction, and P delta V is the work done by the expanding gases produced by the reaction. Which leads us to the next step in understanding enthalpy. Since internal energy is a combination of heat plus work, and we've defined work as negative P delta V, we can substitute these two equations into the enthalpy equation, where delta is equal to Q plus W, P delta V is negative W, negative work. When you add Q plus W minus W, you simply get Q. So the enthalpy of the reaction, delta H, is equal to the amount of heat given off by the reaction when the reaction is done at constant pressure in an open vessel. So if the reaction gives off heat, it's called exothermic. If the reaction requires heat to be pumped into it, then it's endothermic. And the change in enthalpy is always the enthalpy of the products minus enthalpy of the reactants, where delta H is the heat of the reaction.